Hi everyone. According to Chaos reports in 2015, only 40% of projects were on time. There are many reasons, but one of them is bad planning. If you fail to plan, you are simply planning to fail. So planning a project without considering existing tasks, employee availability, contracts, time off, public holidays, and task dependencies will simply lead to a poorly organized project. So this view is simply a Gantt view, and if task 1 is blocking task 2, means that task 1 should be finished before starting task 2. It's simply a dependency, and we display a gray arrow between task 1 and task 2. So it's a respected dependency. But if we try to schedule task 2 before the end of task 1, it's displayed in red, and it's a blocked dependency or a dependency with conflict. If our employee is working 8 hours a day and we are assigning one or many tasks with more than 8 hours, we are forcing the employee to overwork. So this is poorly organized project because it's red everywhere. So today, we're gonna see in depth how with a simple click, we move from this poorly organized project organization to this one. My name is Abdurrauf Ghrisi, software developer at Odoo, and I added the pad for you, so don't hesitate to scan the QR code and ask any question. Now, the goal of the session is simply, if you are an Odoo developer working on project scope, maybe one day you will need to fix some bug or to add some custom features for your customer, so you will deal with this implementation. And if you are an Odoo developer working on any application requiring Gantt dependencies, the implementation was done in Web Gantt, so maybe you will need to inherit some hooks and add your business application logic, but we will deal with it. And simply, if you are a developer or a student coming to discover Odoo, dependencies in general and Gantt dependencies are really common in software industry and in many business applications. So maybe tomorrow or Monday morning, your manager will come with a similar task. It's the summary of 8 months of huge work by services team. So it will be an educational presentation. You will learn some new techniques, algorithms, um theories that were invented years ago to tackle similar problems. So it will change the way you think when facing some problems related to dependencies and try to not reinvent the wheel and use what people have already done. So let's get started. Our example for today is simply this project. In computer science, this shape is called a graph. So it's a set of nodes. In this presentation, they are tasks. Tasks are linked by dependencies, and there are edges between tasks. So this specific graph is called a DAG. It's a directed acyclic graph. DAG, or directed because edges between tasks are in one direction. So if the arrow is going from 1 to 2, means that 1 is blocking 2. Acyclic because it doesn't make any sense to have a loop in project planning. It will never be ended. So there are no cycles and the graph because it's simply a graph. Now, in functional point of view, so task 0 is blocking task 1, but task 1 is planned before task 0. It's a conflict. So you can say, okay, I will solve it easily by moving task 1 after task 0. Congratulations, you solved a local problem, but you created 4 or 5 more problems because now task 1 is blocking task 2, but task 2 is planned before task 1. Same for task 3. You can see that task 1 and task 7 P1 are overlapping. Task 1, task 5, and task 4 are simply executed in parallel, so your employee is forced to work more than expected. So it's not really random or simple to just move tasks. We need the strategy to do it. That's why our first step is to identify tasks to move. So, as we said, it's a graph. There are two main algorithms in graph theory to traverse a graph. The first one is called a BFS. It's breadth first search, and a DFS, which is depth first search. You don't need to master graph theory to follow this presentation. It's educational, so the goal is to introduce this concept for you. You can go after the presentation on the internet and get deeper into details. So DFS is simply we start traversing our graph from the node that should move. So we should move 1 after 0, but we need to check the impact of moving 1. So imagine that 1 moved after 0, but created some conflict with its children, 2 and 3 in this example. We need also to move 2 and 3. After moving 2, we need to check if 5 is still valid, or we should also move 5. So that's the strategy that we will follow. And we stop our DFS when we come to a specific node called leaf. Leaf is simply a node where there are no coming nodes or children, so we simply can stop our algorithm. And it's also an opportunity to check if we have a cycle by mistake, and we need to display a warning to say it's a bad planning. Now we fixed the issue of which tasks should move. Let's move to how can we solve planning tasks without overlapping the employee or overloading the employee schedule. So we need to get something called valid intervals per user. So simply we get the company calendar, for sure in intersection with the company contract, and then we start to remove ranges where the employee is not supposed to work, like public holidays, ranges where the employee is busy doing other tasks, and time off. So finally, we get a set of ranges. They're sorted. It's really important. And we are sure that the employee is available to work during this time. Then we have another issue, which is task duration. Imagine moving a task from Monday to Tuesday. So if we compute duration like as end date minus start date, it's simply 38 hours. But the employee is working only for 24 hours a day, and maybe he's doing some task on Monday afternoon, and he's off on Tuesday morning. So the real duration should be the intersection between task dates and the availabilities of the employee. So in this case, it's only 8 hours. Last but not least, it's just the last step before starting to run the algorithm. So we compute something called first possible date and in degree. Don't worry, I will explain. First possible date is simply, in this example, 7 is blocked by 7p1 and 7p2. For some reasons, when moving all blue tasks, maybe I have some availability to plan task 7 earlier before 7p1 and 7p2. But this will lead to create to conflicts. So when planning again, I need to keep the information that task 7 cannot be planned before task 7p1 and 7p2. So the first possible date to plan task 7, even if the employee is available before, should be the max of end dates between 7p1 and 7p2. You may ask, 5 also is blocking 7, so why can't we get the end date of task 5? Because all blue tasks should move. So the end date of task 5 will change when replanning it. And then we're going to update the first possible date in real time. So for task 7, it's, for example, Friday. And then for all tasks, it's false because, as you can see, all blue tasks are not blocked by any other task. Finally, the in degree. In degree is simple, the number of blocking tasks for a certain task that are not yet moved. In this example, for 1, as you can see, it's not blocked by any blue task. So in degree equals 0. For 2, 3, 4, 5, 6, 7, 8, it's 1 because all these nodes are blocked by only one task. Blocked means that I need to wait to my previous task to be planned to be able to be planned to plan the task. So for task 4, it's different. It's 2 because it should wait for 5 and 3. This term of in degree is really important to achieve some valid order when planning tasks and when moving them. We're done. Let's start our planning. So the important part that, as I said at the beginning, try to not reinvent the wheel. People worked on some algorithm before called Kahn's algorithm for topological sorting. So getting a valid order is simply called topological order. And this algorithm is executed on directed acyclic graphs like this one, and we're going to simply use it. So let's summarize. We have in degree for each task. We have first date. We have the valid ranges for the employee. We set a pointer at the beginning of the first range. Task durations, for simplicity, let's consider that they are all planned for 4 hours. And also, you can see that all intervals are for 4 hours to make it simple to run the algorithm. And then Kahn's algorithm uses a queue, which is first in, first out data structure. So at the beginning, we push all tasks with in degree equals 0, meaning that they are not blocked by any other tasks, so they are ready to be planned. For our case, it's only one. So we push on the one on the queue, and then we pop it. We schedule it on the interval where my pointer is pointing. I update first in degree of all coming tasks because, as you can see, one is blocking 2 and 3. So one is planned. It's no more blocking 2 and 3. We can change or update their in degree. Now it's 0 for 2 and 3. We can simply push them in the queue, advance our pointer, and first date, it should be updated because 2 and 3 should not be planned before the end date of task 1. So we continue, we pop 2, we plan it, we advance our pointer, we update in degree of task 4, now it's 1. We still wait for task 5 to be planned to be able to plan task 2, task 4. We update first date, so task 4 cannot be planned before the end date of 2. We pop 3, we plan it, we advance our pointer, we update the in degree of 5, now it's 0. 0 means that it's ready for planning. We push it in the queue, we pop it, we advance. And now, this is an interesting case where 5 is planned, so we can plan 4 because in degree now is 0. We updated first date, which is Tuesday, 5 p.m. And for 7, we cannot update because Friday is already after Tuesday. So for a certain reason, it's random because I can visit 7 before 4 or 4 before 7. So imagine that 7 is pushed before 4 in the queue. So 7 cannot be planned in this valid interval. I need to skip it and go to the last interval. I plan 7, but I no more have intervals to plan. 4 is no more planned. I have skipped one interval and my pointer is just going to the left, so to the right, so I cannot go back to use that skipped one. So it's simply an inefficient planning. Can we do better? Let's see. As I said, if 4 was pushed before 7, I could achieve a better and optimized planning. But it's a bit random. I can't rely on something that will change according to the order of the DFS or the push in my queue. So I need something more consistent. That's why we moved from a queue to something called min heap, or if you are a big fan of C++ like me, it's called priority queue. So instead of just pushing tasks without any priority, I will say that instead of blocking a task after a task, another task that should be delayed, I will add the first possible date. And the importance of using a min heap, it's a data structure that it's sorted. So when you push, it's in logarithmic time, but it's sorted every time. So when I push 4 and 7, 4 will be usually at the top because it can be planned before the second task. We got the idea of using a priority queue from a known algorithm in graph theory, which is called Dijkstra for shortest path. You don't need to master the algorithm. The goal of the session is it's an educational session, so I tried to add some keywords. Maybe you have a similar problem, so when you go home, you can watch the video again, look to the algorithm on the internet. Maybe it can solve your problem. You don't need to master it. Now, let's get a more complicated example. So if you have multi-users with multiple valid users per employee, and we have an issue when all what I presented is now on 17.4, so you can check the code if you have access to enterprise. But The limitation with this implementation, when we have multi-users and if we have a task assigned to both user 1 and user 2, we decided to follow the company calendar. Good idea or not, let's see. The company is working on Thursday, so we can take it as an available uh, interval and plan our task. But user 2 is on time off and user 1 is busy. So I'm simply overloading the employee. At 18, you will see that we introduced something called valid intersection. So instead of just following the company calendar, we start to check intersections where both employees are free. So in this case, the task will be planned from Monday to Thursday, but with allocated hours equal 16, 8 for each one. That's why we introduced something called valid intervals per group. So at the beginning, when we pre-process and prepare our data to run the algorithm, we create an interval for both user 1 and user 2 with only their intersections. So, but is the previous implementation still valid? We can simply run it again and look for maybe a corner case. We set our pointers at the beginning of all intervals. We receive task 1, we plan it for user 2. We receive task 2 for both user 1 and user 2, so we plan it. But when we receive task 3, at this level, we are no more sure that when we advance our pointer, all incoming intervals are still valid. So because this one was used to plan task 2. And that's the problem. One solution maybe is to, okay, I will move to the end of task 2 and plan directly task 3. Okay, no conflicts, but you skipped 3 intervals, so it's not optimized. The solution was, let's remember that ranges are usually sorted. So at a certain point, I can use any sorted data structure like a set or a min heap, or maybe do some binary searching to find if this interval is still valid or not. We implemented, it was fast, but the problem is it was too complex. Even for you following, maybe it's a bit overwhelming, maybe you are a bit lost, too much details. So the implementation was really complex. The code starts to be a bit difficult to read. The complexity may result in more time needed to understand, debug, and maintain by any internal developer or a developer from the community. So a large amount of code increases the risk of introducing bugs. And we did a small benchmarking with a typical conflict to solve with maximum 50 tasks to plan. The execution time difference between the implementation that I presented and the final solution that I will explain later was 300 milliseconds. However, when we populated larger projects, this could lead to performance issues. So actually, it's a new feature. We don't know the size of projects that will move. So we need a valid reason and a pain point to introduce some complexity in the code because actually we don't know the size of projects. So if needed, the most important point that now we work with 8 months on this feature. We master the topic. We know all possible or maybe some possible solutions. We know the limitation of each one. So in case of any issue problem, we are ready to implement to re-implement the optimized one in maybe some weeks. The final solution was simply, and the goal was to make the code clear. It's we removed the pointers concept. When we plan task 2, for example, for user 1 and 2, we remove these used ranges in all intervals where user 1 and user 2 are implicated. So thank you for your attention. And if you have any question, don't hesitate to add it to the pad.
Hi there. Thank you very much for the very interesting talk.
Thank you.
So far there are not many questions on the pad, so
Okay.
feel free to scan the QR code and add any questions that you might have. I'll quickly check if they are on the YouTube channel. I don't know if there's anything else you'd like to
No,
add.
I think
No?
it's all.
Okay,
Okay.
perfect. If there are no more questions, then thank you very much for your attention.
Okay.
We're getting a thank you message that it was very clear.
Okay,
So
thank you. Thank you.
thank you very much.
Thank you.